Calculate then the work done by all the forces, right? It's the work done by the net force. And that's just, it's the net force divided with the infinitesimal displacement, right? But now I'm going to use that expression, right? So then this will be, I'll just write an equal sign over here. This will be MA over 1 minus v squared over c squared to the 3/2 times the r, right? And I'll do the same thing. The m goes outside. Now, the v may be changing, right? And so I'm going to keep that term inside the integrand. So this is a added with the r. Then I have 1 minus v squared over c squared to the 3/2. Now, what about this numerator? So just like in what I just did a little while ago, right? A divided with dr is dv dt divided with dr, but dr dt is v, so this is just v dot dv. So this expression becomes m times, and then v dot dv, 1 minus v squared over c squared. And let's say that I start from 0, and then up to some final speed v. Just call it v, or v final. Let me call it v final. So we gotta do that integral. So we can do a substitution. Let's say y be 1 minus v squared over c squared. I'm just gonna let this whole thing in the denominator without the 3/2. I'll just call it y. Right? I'm just gonna make that substitution. So what is the y dv? It's minus 2v over c squared, correct? So that means that dy equals, or yeah, dy equals minus 2v over c squared times dv. If I bring the dv over to that side, right? But notice that I have a v dv in here, right? So from over here, what is v dv? It's minus c squared over 2 dy, correct? Yes? So I'm going to take that and I'll put it in there. So this becomes, I have a mass outside over here, integral. Instead of v dv, I'm going to write minus c squared over 2 dy. And then I have in the denominator, well, all of this was y, right? This is y to the 3/2. So the minus, the c squared, and the 2, those are constants. And then I'll just write this as that. Correct? And this is an elementary integral, right? Minus mc squared over 2. And that should be what? Y to the minus 3/2 plus 1/2 is minus 1/2 over minus 1/2, correct? So this minus sign and this minus sign cancel. This 2 cancels that 2. And I just get mc squared, and then y to the minus 1/2 is just the square root of y. Right? So I'm going to continue here. So I still have work done by all the forces on the left-hand side equals, and now I'm going to go back to what I had substituted in, right? I said that y was this, right? So I'm going to take that. Now I'm going to, substitute it back. So I get mc squared over the square root of 1 minus v squared over c squared. And now I'm going to evaluate my limits that I initially had over here, right? So this is, I'm going to evaluate it from, starting from rest, let's say, to some final velocity or final speed. So this becomes mc squared, and then this is 1 minus v squared final over c squared, right? Minus, and then when I plug 0 in here, this goes to 0. 1 minus 0 is 1, square root of 1 is 1, so I just get a c squared. Right? And this is the work done by all the forces. And this is equal to is the change in kinetic energy, which would be kinetic energy final minus kinetic energy initial. But in this particular problem, right, I just chose the initial kinetic energy to be 0. So in this particular derivation, this is 0. So therefore, right, the work done by all the forces is just the final kinetic energy, because I let the initial kinetic energy be 0. So this is the final kinetic energy is therefore equal to mc squared over 1 minus v final squared over c squared, square root of that, minus mc squared. And if I just drop the final, I get this. Right? The kinetic energy of the particle of mass m when it's moving at speed v is given by this expression. Now, you might say, but what happens if you take this expression and you take the limit as the speed goes to 0? You might say, that you get the wrong result, because we're supposed to get 1/2 mv squared, which is supposed to work when the speed of the object is small compared to the speed of light in vacuum. And you might, at first glance, say, well, if I let v become very small, then this goes to 0. 1 minus 0 is 1, square root of 1 is 1, mc squared over 1 is mc squared minus mc squared. I get 0. So if the thing is moving at 60 miles an hour, does that mean the kinetic energy is 0? So we have to be careful. So let's do this. So this is the expression by Einstein, right? The kinetic energy is defined as mc squared over the square root of 1 minus v squared over c squared, but then you have to take this out. That's the kinetic energy. Now, if v is much less than c, like a car, a baseball, right? Does that mean that that kinetic energy is 0? The answer is no. Then, so this becomes, I'm going to write it like this. 1 minus v squared over c squared to the minus 1/2 minus mc squared. And this quantity is small, right? So from math, you learn that if you have 1 plus a small number raised to the nth power, and that small number, you got 1 plus or minus a small number, if that small number is much less than 1, if this is much less than 1, then this expression approximates to 1 plus nx plus nx n minus 1 x squared over 2 factorial plus n minus 1 n minus 2 x cubed over 3 factorial, blah, blah, blah. Taylor's, the binomial expansion. So this becomes, in the limit, right? So that's an equals. Now I'm going to make the approximation now. This is mc squared. Now, what about this? If x is much less than 1, notice that the first correction is nx, the exponent times a small thing, and then, but then that x gets squared, and then it gets cubed. And they're very small, right? So we might as well just throw them away. So then this becomes, essentially, 1 plus nx, right? And plus terms that you throw away. So it's 1 plus the exponent multiplied by the small thing. So this is 1 plus the exponent, minus 1/2, multiplied by the small thing, which is minus v squared over c squared, plus the other terms that we throw away. And then minus mc squared. Now this is an approximation in the limit that the speed of the object is small compared to the speed of light in vacuum. So therefore this becomes, now I'm going to multiply through mc squared times 1 plus mc squared. This minus times this minus gives me a plus, and I have a 1/2 v squared over c squared. In fact, how about we keep the other terms? Let me just keep another term in here, right? Let me keep the next term. Let me not throw it away for fun. And then those I'm going to throw away. So I'm going to keep that other one, right? Okay, so what would that be? Plus n is the exponent, which is minus 1/2. N minus 1, so how much is minus 1/2 minus 1? Minus 3/2, right? And then the small thing squared, so the small thing minus v squared over c squared divided by 2 factorial, which is divided by 2, plus blah, blah, blah. So now I have, and of course, all of this minus mc squared. So mc squared times 1 is this. Mc squared times this minus and this minus gives me a plus. So I have mc squared 1/2 v squared over c squared. Mc squared 1/2 v squared over c squared. And then that's that, right? Plus, I have mc squared times, times what? I have, let's see, this minus sign squared gives me a plus. This minus and this minus gives me a plus. I have downstairs, what do I have? 2 times 2 times 2 is an 8th. And I have a 3 upstairs, so I get a 3/8 over here. And I have a v squared to the square, which is v to the 4th, and I have c to the 4th. I said 4th, but I wrote 2. Plus the other terms that I throw away, minus mc squared. And notice that this guy cancels this. So the kinetic energy becomes, well, this c squared cancels that c squared, and I get 1/2 mv squared. If you just get the first correction, you get, Newton's expression, 1/2 mv squared. But in fact, there is another correction, right? Which in Phys 185 we don't use. We just never say, oh, it should also be this. This is the next order correction. So I put a plus over here. It should be times, right? It should be times, right? I put a plus over here. So it should be mc squared times this. So, I mean, that was a plus, but I put a plus, but it's supposed to be times it. So correction over here, right? And then I have c squared cancels c to the 4th, so I get a c squared downstairs. So I get 3/8 m v to the 4th power over c squared. And then other terms. This is kinetic energy. It's the energy associated with the motion of the object, plus other terms. Now, in Phys 185, and usually this term is much bigger than this term, so you just throw that out. Yes. So, or this goes to kinetic energy is 1/2 mv squared. The point is that what I'm trying to say is that kinetic energy, once this mc squared cancels the 1 with this one, all the other terms, that's the kinetic energy, because that's the energy associated with the speed of the object. We just cut it to one term in Phys 185, and we just say 1/2 mv squared. But in reality, there are other terms. Now, so that's done in my notes, but I wanted to do it on the board to show you that you don't need really, I mean, yes, I don't know, do they teach you the binomial expansion in high school? Maybe they teach you how to derive it in calculus, right? With it's a Taylor series or Maclaurin series, right? So they teach you how to derive it in when you take calculus, right? But I don't know if you ever use it in high school. I just don't remember me using it. Maybe I saw it, but I never paid attention to it.
First time I remember it was tough too.
What's that?
At least you use it with integer powers. So like.
You use it what?
With integer powers, like it's like 2, 3, 4.
Oh, okay. Mm-hmm. See, I never took. Was that in like pre-calculus?
I think like either algebra 2 or pre-calculus.
Either what?
Algebra 2.
Algebra 2?
Or pre-calculus.
Yeah, I never took pre-calculus, so I don't know. It's a course that I was just. So you know things that I don't know from math. You must have learned stuff in pre-calculus that I just never learned. I never took it. They didn't want to offer a pre-calculus class in my high school. There were only 2 of us interested in taking pre-calculus. It was a high school in the South Bronx, so it's like, I remember, I took algebra in the 9th year.